This is the world's largest earthquake
Gerai, bet jo, čia didžiausias pasaulio žemės drebėjimų simuliatorius.
simulator. It's called E-Defense. Its huge shake table can support a 10-story building, and then move it in all directions with the force of the world's most destructive earthquakes. E-Defense has conducted more than 100 tests, subjecting all kinds of buildings to different simulated earthquakes, all to learn how to make buildings more earthquake resistant.
Įdomiai.
Part of this video was brought to you by Shopify. More about them later in the video. On the 17th of January 1995 at 5:46 in the morning, an earthquake struck the city of Kobe, Japan. It took everyone by surprise. Japan is one of the most seismically active countries in the world. It sits on the boundary of 4 tectonic...
Aš kaip tik žiūrėjau užvakar, off-stream žiūrėjau dokumentiką apie tą tsunami, kur buvo Japonijoje irgi po to 9, kiek ten buvo tas skalių žemės drebėjimas, kur ten paskui ir Fukushima reaktoriai, ten tie sugriuvo, kai kurie, nežinau, ten dalys jų sugriuvo. Tai čia dabar sutapimas toks.
Plates, and 90% of all earthquakes and almost all of the powerful ones happen at tectonic plate boundaries. But Kobe isn't near one. This earthquake was caused by an intraplate fault, essentially a crack in the Earth's surface that isn't at the boundary of a tectonic plate.
Oh, įdomi.
This fault hadn't produced any earthquakes for around 1,000 years, so the city was completely unprepared. The quake measured a magnitude 6.9, just under the definition of a major earthquake. Despite this, the earthquake killed more than 6,000 people and left another 300,000 homeless. More than 80% of the fatalities were caused by the collapse of buildings. The total economic cost was estimated at $80 billion. In response, the government gathered scientists for a conference on earthquake disaster prevention, and there they agreed to build the largest earthquake simulator the world had ever seen.
Damn.
So I sent Peter to Japan for an exclusive look inside this facility.
So we're entering the world's biggest earthquake simulator as they're about to do an experiment. So let's go. Right now there's 8 concrete walls that they're going to feed seismic signals into the shake table, and they're going to see which ones are the most sturdy. So the seismic data that they're going to feed in is from the El Centro earthquake, which was an earthquake that happened on the 18th of May 1940. It was a 6.9 magnitude earthquake, and it's one of the first ones that we actually have seismic data from. Whoa. Okay, things are moving. Wow, 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 wow. Wow, oh.
Damn.
Okay, it's just really cool to see such a big structure kind of moving that.
Kas man yra biški fascinating, nu, čia matom kaip platforma juda, bet realiai žemė taip pat juda, nes nu, tie patys duomenys tipo. Damn. Bet jo, žemės nu, tas paviršius tipo actually juda to, ir judina visus dalykus, kurie ant jos pastatyti. Fascinating yra.
Far and that fast. Wow.
The first test that
Pavėlavai biški Karalius su to Ask Jesus, jau kiek jau mėnesiais jis veikia, ten vienas iš Atėnės projektų.
So white noise is just all different frequencies, low frequencies, high frequencies, everything in between.
They make this big deal. They're like, oh, 1 minute, like, and then they do like the 10-second countdown.
3, 2, 1.
And then it's just like functionally nothing.
We flew all the way to Japan to see this, so let's hope at least one wall falls down.
And I couldn't figure out why for a long time.
All the structure has natural frequency. When the structure is damaged, natural frequency becomes shorter. So by inputting white noise with components of wide range of frequency, so we can find natural frequency of building.
Oh.
So first, okay, input white noise first.
Ten natural frequency tai ta priežastis, kodėl tas tiltas sugriuvo tada senas tas. kur pradėjo visas vinguoti, nes kaip ten oro vibracijos ar kažkas atitiko to tilto medžiagų natūralią tą vibracijos, tą dažnį kažkokį ir dėl to liktais taip ten paaiškino. Prisimena tą tiltą? Kaip tas tiltas? Le. Tacoma Bridge Collapse, Wobbly's Bridge, ar čia šitas? Jo, šitas.
Which increases with each swing. Only a 35-mile-an-hour wind is blowing, but this apparently sets up a rhythmic swinging of the bridge, which increases with each swing.
Tas fascinating, to tilto istorija buvo.
And after that, input earthquake motion, and then we usually input another white noise. So we can find the change of natural frequency.
At the center of E-Defense is a 20-meter by 15-meter shake table, which weighs 800 tons. On each side there are 5 hydraulic actuators which push the table side to side, and the whole thing is supported by another 14 actuators at the bottom which move the table up and down. The whole facility is massive. There is one warehouse where the shake table is housed, but it's in such high demand that all the buildings are constructed in a separate warehouse and then transferred across. Then there is a whole area full of giant engines and nitrogen storage tanks just to power the shake table.
Oh my god, this is a huge engine.
Using this setup, scientists can perfectly simulate past earthquakes and determine their effects on different buildings. The shake table can hold masses up to 1,200 tons and jolt them with accelerations up to 15 meters per second squared. That's over 1.5 Gs.
Man vis tiek yra netikėtina, kaip tie dangoraižiai fucking nesugriūna. Nu, aš matęs, aš domėjęs daug, kaip jie pastatyti, man neįtikėtina. Man smegenis supranta, bet tiesiog vis tiek yra magija vos ne. Nu, ne magija, bet, nu, absurdiškai nuostabus pasiekimas inžinerijos, vėlgi šiandien tematika, dangoraižiai pastatyti ir jie fucking woblina belenkaip ir negriūna. Jie tam specialiai skurti, kad būtų atsparus žemės drebėjimams ir panašiai. Nu, belenkas.
Fighters can pull like 10 Gs as they turn, but it's another story if you're in your house and the floor starts accelerating faster than a falling object. The goal of the shake table is to realistically simulate earthquake.
Aš esu matęs, ble, daug jų, aš nežinau, kurį aš čia jungsiu. Pavyzdžiui, 9,1 earthquake. Čia gal labai gerai nesimatys, kiek juda tie dangoraižiai. Ne, čia žiauriai gerai nesimatė. Ne, čia iliustracija labiau. Ar čia sugriuvimo parodys? Ne, nežinau, ką čia parodys. Nenoriu, muziką nežinau. Building under construction. Ai, čia dar net nepastatytas. 7,1 Richterio skaliai drebėjimas. Unreal. Jesus Christ. Ir kai tu esi inžinierius, kuris tą pastatė, tu žiūri tą ir tu žinai, kad jis nesugrius. Žmogus random žiūrėtų, aš gyvai pamatyčiau, holy shit, su kiekvienu swingu galvoju, ar sekantis kartas nugriusis. Šiaip atrodo smarkiai per daug, negu bet koks solidus pastatas galėtų fucking woblint. Ja, aš nežinau, kodėl man tiek fascinating yra tie dangoraižiai ir žemės drebėjimai ir apsitai kiek jie juda ir... Okay, gerai, žiūrim toliau video.
To do this, you need two things: a way of being able to apply enough force in a precise and controlled way, and the signal data from real earthquakes. This is how they do it.
Are you okay at high elevation place?
Let's see.
So this one is actuator.
The actuators themselves are hydraulic. Inside each one, there's a 30-ton piston driven by high-pressure oil.
This is massive. This is, I don't know, a meter and a half in diameter?
But to generate the pressure needed to operate the shake table and sustain it for minutes at a time, E-Defense needs huge reserves of pressure storage. That's why there's a whole section of the warehouse with massive high-pressure storage tanks full of nitrogen.
We have 20 of these red spherical shape accumulators. So we accumulate the pressure.
To pressurize these tanks, liquid nitrogen is pumped in from a large storage tank outside, and as that liquid warms up, it turns into a gas and expands 694 times its original volume. It's relatively easy to obtain very high pressures with nitrogen. Then, when the pressure is needed, it's transferred to the oil using a bunch of pistons. As the test runs, the oil is pumped to the actuators by these giant engines, but even they can't sustain the pressure needed to operate the shake table for very long. And so the nitrogen pressure reserves mean that the shake table can deliver a consistent amount of force from the start of the test right to the end. While a test is run, the pressurized oil needs to be pumped to the actuators by the engines. The flow to each actuator is controlled by electronic servo valves, meaning precisely timed and measured forces can be applied to the table to match any earthquake. Now, because the actuators can only move in one dimension, if they were fixed directly to the table, there would be no flexibility and they would break. And so the engineers at E-Defense designed bespoke 7-meter-long universal joints to transfer the force from the actuators to the shake table. To simulate real earthquakes, the shaking can't be random. I mean, each earthquake has its own characteristic pattern of movement, which can be recorded using a seismometer. Early seismometers were basically just a pen attached to some springs, drawing a line over a moving roll of paper. And when there was an earthquake, the pen would shake and draw out the pattern of acceleration of that earthquake. The trace that was seen on the paper is known as a seismograph. Nowadays, we use geophones. A geophone is made from a coil of wire suspended around a magnet, all held together by springs. When the ground shakes, the springs shake, causing the wire to move up and down over the magnet, which generates a current. This current is recorded to produce a seismograph. To get the full picture of how the Earth's surface moves in all 3 dimensions, 3 geophones are needed, one oriented in each orthogonal direction. The strength of an earthquake is measured on the magnitude scale. The smallest earthquake that humans can feel is about 1 billion times less powerful than the biggest earthquake ever recorded. Because of this, the magnitude scale is logarithmic. An increase of 1 on the magnitude scale represents a 10-fold increase in the force of the earthquake.
Oh.
An earthquake under 2.5 on the magnitude scale is imperceptible to humans. These happen millions of times every year, but can only be detected by geophones. Earthquakes higher than 6 on the magnitude scale can damage buildings, but occur far less frequently, only a few hundred times a year globally. The most powerful earthquake ever recorded was the Great Chilean Earthquake of 1960, which measured 9.5 on the magnitude scale. It killed somewhere between 1 and 6,000 people and caused more than $400 million worth of damage. But how destructive an earthquake isn't just determined by the magnitude. It also matters how close the epicenter is.
Behind me is what was until 2022 the world's longest suspension bridge. The Akashi Kaikyo Bridge connects Honshu, the main island of Japan, to Awaji Island, nearly 4 kilometers away. The center span, the distance between the 2 towers, is 1,990 meters and 80 centimeters. I'm here because a few kilometers that way and 16 kilometers underground was the epicenter for the great Hanshin earthquake of 1995. As the earthquake struck, the bridge was still under construction, and despite being right above the epicenter, there was no major damage to the structure. But the earth underneath the bridge had moved and the original plans would no longer work. The plans would need to be modified. So that's how the world's longest suspension bridge became 80 centimeters longer.
After E-Defense opened in 2005, one of their first tests was a comparison between 2 traditional Japanese wooden houses. The houses were transported from the nearby city of Akashi. They were rebuilt on the table and shaken at the magnitude of the Kobe earthquake.
Oh no. No
The house
shot.
that stayed up had been retrofitted with wooden braces, beams, and metal joints, making it more earthquake resistant. The other was unmodified. This test demonstrated that older Japanese houses are not able to withstand powerful earthquakes. It also presented a solution. Some relatively simple and inexpensive structural reinforcement can significantly increase earthquake resistance.
In 1981, the Japanese government
Čia paskutinis tas buvo, kai Turkijoje buvo žemės drebėjimas ir ten apie tai labai diskutavo, kad tipo turėjo būti ir kaip turėjo būti, bet nepadarė dėl korupcijos, atrodo, ten tie sustiprinimai ir panašiai. Arba ten netgi statė namus tos, kurie nėra labai gerai atsparus tie žemės drebėjimai, vėlgi dėl korupcijos ir kainų skirtumų ir panašiai. Bet jo masyvus skirtumas.
uses like all these new building codes.
Jo, žiūrėjom tos video, kur ten sugriauti visai rajonai buvo, kur namai biškai.
You need these isolation things, you need these like wooden beams. Of the buildings that were built post 1981 in Kobe, 0.3% of them collapsed during this earthquake. Of the ones that didn't, 8.4%. Like about a 30-time difference between new houses and old houses, right? This is kind of like weird thing. Like I was there on day one, you know, watching like the shake table work, and I'm just kind of like looking around this entire, like this giant warehouse, and I see this section where it's just like what looks like IKEA furniture.
Can you tell me what this is for?
To see the in-room safety, we place lots of furniture in the structural specimen.
A lot of the injuries, right, that happen in earthquakes is from stuff falling on top of you.
I know, makes sense, yeah.
A cabinet
Nekontroliuoji nieko, chaosas.
hitting your head, or you know, you being crushed by a fridge or something like that. Half of the injuries that were sustained indoors in Kobe were from, you know, furniture falling on top of people. So one of the things that e-defense does is like, how do you make sure buildings don't collapse, but it's also how do you make sure that the insides of the buildings are also safe.
Čia atrodo daug sunkiau būtų sukontroliuoti random.
This part of the video was brought to you by Shopify. You know, back in 2015, I came up with Snatoms, a better way of modeling molecules, and I've been using Shopify to sell Snatoms ever since. And over those last 8 years, I found Shopify really easy to work with. They offer an all-in-one commerce platform that anyone can use to sell products, manage inventory, or grow their business. One of my favorite things about Shopify is the depth of data that they provide. You can see real-time data on how many people are on your site at any given time, and how many are checking out. Plus, from the analytics, I can learn which products are selling and when. There are more than 8,000 easy-to-use apps with ad tracking, integrating your shop with TikTok or
šitą reklamą. Šiaip dažniausiai, kai žiūriu angliškus video, daug mažiau žmonių būna, nes nėra žmonėm įdomu, nes nežinau iš tikrųjų kodėl. Gal angliškus video aš kai žiūriu, yra labai specifiniai tipai video, kokius aš žiūriu, kur daug kam nėra labai įdomu. Tipo, geriau, žinai, lėkštutės įjungčiau ir iškart daugiau, bet žiūriu, jūsų gan daug, virš 40, tai čia... Reiškia, priprato žmonės, arba pasikeitė žmonės ir daugiau žiūri tiem, kuriem irgi įdomu tokie.
Or automatically recommending frequently bought products. Despite it being so powerful, Shopify is incredibly easy to use. So if you're just starting out your business or side hustle, or if you want to make the sales process more efficient,
jo, aš ir galvočiau, kad baldų tu nelabai sukontroliuosi, bet va, gal kažką išmąsto.
Millions of businesses in 175 countries. Seriously, Shopify is great. And for a free trial, you can go to shopify.com/veritasium or just scan this QR code.
Sakiau, okay,
there is a link for that in the description too. So I want to thank Shopify for sponsoring this part of the video, and now back to earthquakes.
So for this next test, they're going to feed in the seismic signals from the Great Hanshin earthquake, which is also known as the Kobe earthquake. It only lasted for about 20 seconds, but it had a magnitude of 6.9, and the maximum acceleration was about 0.9 G, which is, you know, kind of crazy to think about for an earthquake.
Bet čia Bet tas pats footage.
Go. Oh boy. That rumble. Oh man. Oh, the whole building is, oh my god. How short
okay,
that was,
anticlimactic.
how powerful that was. Boy, earthquakes are no joke.
That's a nice way to observe an earthquake. Like, how else can you observe an earthquake without being subject to that shaking, right? No one has got to experience the Kobe earthquake from like just right beside it, but not shaking.
O tai baldai.
In Kobe earthquake, we recorded very, very large motion, but it's very short. But in 2011...
Iš yra geriausiai tiems, kurie baldų neturi. Žinai, kai ten viengungiai gyvena ten Amerikoje, kur rodo, žinai, tą čiužnį pasistato, net lovos freimo neturi ir viskas, stalas gal su kompu, daug dievė, viskas, tipo, geriausiai jiems. Nėra šans, kad užkris kažkas, nes nieko neturi. Tai tiesiog išvada vienintelė, reikia neduoti žmonėms užsidirbti, kai visi ubagai būtų. Ir mes taip juos apsaugojam nuo žemės drebėjimo pasiekmių. My logic is undeniable.
Japan earthquake, we recorded very, very long duration motion, like 5 minutes. And the bottom one is earthquake. In future Tokai Tonaka earthquake. So we are expecting very, very long duration motion.
How do you predict?
Plačia buvo iš iRobot filmo? Yeah, my logic is undeniable. Kaip ten... Vava.
My logic is undeniable.
I fucking love it. Aš tą filmą gal 10 kartų mačiau.
What kind of earthquake you're going to get?
Ask seismologist.
I will ask seismologist.
I'm sorry about that.
No, that's good. That's good.
Seismologists give a 70% chance that a magnitude 8 earthquake will occur somewhere near the Tokai region, home to more than 15 million people, within the next 30 years.
Damn.
The Nankai Trough, located off the southeast coast of Japan, is where the Eurasian plate pushes against the Philippine plate and produces a massive earthquake every 100 years or so. But the Tokai region hasn't experienced such an earthquake in over 160 years. The government estimates that more than 320,000 people could lose their lives. Most fatalities will likely be caused by the 30-meter tsunami, but a quarter, around 82,000, could result from building collapse. This is why earthquake preparedness is such a big deal.
Newly built buildings are very, very safe. They have very high seismic performance. So even in a very, very large earthquake, these buildings can survive.
Except in extreme cases, most new buildings in Japan can survive most large earthquakes. So the next challenge is to keep them functional. Currently, even when buildings don't collapse, water pipes often burst, leaving people without water and electricity.
I know.
And so they still have to leave their homes. This is the next challenge they're trying to solve at E-Defense.
So now we can prevent a fatal collapse. But now we have to think how to prevent this kind of functional loss.
You guys are now at the step that's beyond what I was thinking, right? It's my step was like, how do we make sure that houses don't fall down?
Yeah.
You guys are like, yeah, no, we figured that out. We can make sure that houses don't fall down, more or less. Doing this very important work.
That got us.
You guys are making the world a safer place. You guys are making Japan a safer place. You're updating building codes to make it, so fewer people die.
What I love about the story of E-Defense is that Japan didn't simply wait for more earthquakes to happen and just hope for the best. They spent billions in research to prevent people suffering from these disasters. They realized that while they can't predict the next big earthquake, they can make sure that they are prepared when it does happen.
Vienintelis tas jo, Lietuvoje žemės drebėjimas, kur, aš jaučiau ir prisimenu, tai jo, tas, kur... Ką ten buvo, 4, jo. Mes tą googlinom senai, kažkada jo 2004 buvo ten tas, kur actually jautės. Fucking fascinating. Man atrodo, daugiau jokių ir nebuvo, bent jau tokių, kad pajaustų. Ten, man atrodo, tik ten Klaipėdos tam regione toj pusė tik ir jautės. Ble. Bet jo, vėlgi, Lietuva yra žiauriai gera vieta gyventi. Pas mus čia nėra. Nei žemės drebėjimų, nei ten uraganų visokių, nieko realiai iš tų nėra. Koks
Pink money is the man.